In this video, we're going to work with the exact same function that we had last time, and I'm going to show how to find the derivative using implicit differentiation, and we'll see in this case that we get exactly the same answer regardless of which method we choose. Now, if we want to use implicit differentiation, it's a little bit different than the process for explicit differentiation. Here we said we solve for y and then take the derivative. I'm sort of going to take those steps and switch them around. So instead of taking the derivative last, I'm actually going to start this problem by taking the derivative. This is the thing that makes it really different. We're not actually going to solve for y here. We're just going to start by taking the derivative. And the one thing we need to remember here is that in every single one of these implicit differentiation examples, we're going to be using the chain rule. And the reason for that is we can think about y is a function of x. And when we have something like, as we'll see in our later videos, we might have something like y squared. Well, this is really like saying I have a function of x squared. So we're going to have to use the chain rule here, which means that every time we take the derivative of a term that has a y, we are going to need to multiply by either y prime or multiply by dy over dx, just depending on your preferred notation. Most students that I've worked with so far have kind of preferred y prime, so that's the notation that I'm going to use here. But the shortcut here for the chain rule is anytime I take the derivative of a term that has a y, I'm going to have to multiply by y prime. And just to kind of reiterate that, that's because if I have something like y squared, y is my inside function. So I would say, well, the derivative of that is 2y times y prime. So we're going to start by taking the derivative, and if you're a little unsure about that process, we're going to spend a lot of time in this section with it. So we'll start by taking the derivative, and then once we have our derivative, our second step is to solve for y prime or dy over dx, just depending again on your preferred derivative notation. So we take the derivative first, and then we're actually going to have to solve for that derivative. So if I'm working with a relatively simple function like I was last time, 3x squared plus y minus 2 is equal to 0, I'm just going to start by taking the derivative of this function. Derivative of 3x squared, well, if we have a term that has an x, we're just going to take the derivative of that just like we normally would. So, okay, then here we're going to have 6x. Plus, here, when I take the derivative of a term that has a y, I'm going to sort of think about it, at least initially, as how would I take the derivative of it if I just replaced y with x? Well, in this case, the derivative of x is just 1. But I have to remember I'm using the chain rule, which means I really need to multiply by y prime. So I need to take 1 times y prime. So the derivative of that middle term is going to be 1 times y prime. If you just want to jump straight to y prime, that's also fine here. Negative 2, that's a constant. Its derivative is 0, so we don't need to learn any new rules there. And then the derivative of the other side over here is 0. So what we're actually doing in this first step, and I forgot to do it here, I'm going to try and use this notation more often. And when we take the derivative, I'm going to use the derivative operator. This says the derivative with respect to x. So I am taking the derivative of this function with respect to x. And I'm taking the derivative of both sides here. If I had something that was not 0 over here on this right-hand side, I would have to take the derivative of that right side, as we'll see. But then at this point, okay, we've got 6x plus y prime is equal to 0. Well, here, if we wanted to jump to our step 2 now, we've got our derivative. We just solve for y prime. In this case, we would just subtract 6x from both sides. So y prime is equal to negative 6x, and there is my derivative. Now here, I ended up with exactly the same derivative that I did using explicit differentiation. So for a problem like this, it might not make sense to use implicit differentiation. There's no real benefit to using it here in this case, but there are some situations where if you look at this first step, when we say solve for y, that is going to be either very difficult or in some cases impossible, in which case, if we want to do our cool calculus stuff, that means that implicit differentiation is going to be the only way that we can find a derivative of those types of functions. So it is very, very helpful in those situations.